Stick around to see how we modified this clock so I can send it to a friend in Australia. So we'll cover a modification I had to do to this clock to make it universal, to maybe operate on the over in Australia. Here it is in the USA after I did a modification to the power supply circuit. Okay, so we have the clock opened up now. Just took the top off, and you notice this section over here looks like some work was done. It looks a little bit more modern, put together on a little perf board. So basically what was in here was pretty much a hunk of iron like this. Alright, it had a 6.3 volt AC output. This corner of the board has 4 big rectifier diodes. There is also a big power supply capacitor here, a smaller capacitor over here with a couple resistors for pulse shaping and conditioning to provide the 60 Hertz to the divider section, which is used for the time base, and it gets divided down to the 1 pulse per second to make the seconds count. So that was all done over here: rectification, pulse shaping, conditioning. This big iron transformer sat mounted to the back on this side. Okay, I have a prior video that shows this clock. You could refer to that if you wanted to see what it was before. It goes back a couple years ago in the videos. Maybe I'll link that below. But for this video here, I just wanted to go over the modification that we did. I want to send this to a friend in Australia, and over there we have 220 power with 50 Hertz frequency. This clock would not work over there the way it was. This clock required a typical 2-prong plug to plug this transformer in, and at 115, 120 volts, 60 Hertz. So 2 problems there. The winding of the transformer was not suitable for the 220 over in Australia, and then also the frequency difference creates an issue to be using for the time standard. So this circuit board actually has a jumper in it. Very simple, unsolder, move over, and very easy to set it up for 50 Hertz. So if you're looking at it now, we're plugged in at 60 Hertz. It's counting a little fast. That's why. Okay, so that was pretty easy to adjust. Now, power supply, we're going to make this universal, a little bit more universal. So I removed the big iron transformer and decided to go with a wall wart type transformer. Okay, so now you just grab one locally to your destination over in Australia, for example, and with a standard barrel jack on the back. I think I use a 2.1 millimeter one here, so hopefully that works out where this thing is about to head off to. But 12 volt AC into the back. Okay, so that's why I can use it over here. All I have to do is just move the jumper to 60 Hertz. But over there, it's all set up for the 50 Hertz, and he just has to get his suitable power adapter to be able to plug in the outlets that they have over there. Plug it in the barrel jack in the back, and off you go. So along with that, we had to then work on the rectifier section and power supply. Alright, so I had one of these very oversized, but this rectifier right in the back here, and I'll zoom in on that. And bridge rectifier in the back comes in the barrel jack, 2 AC lines up to that, and then over there out with the DC and to the big filter cap over here. Now we have a Murata switching regulator on here. Okay, The prior circuit, as it was before I tore it down, did not have regulation. What it did have was a 6.3 volt winding and a very crude pair of 1 ohm resistors that dropped the voltage down for the logic circuit and the display tubes. It actually did run a little higher voltage. It was over like about 5.5 volts, really pushing the TTL logic, which requires a very tightly regulated 5 volt supply. Somehow or another it worked for many years. A 1975 circuit design. So we improved on that. So now we have the Murata switching regulator in there, which tightly regulates this thing very close to 5 volts. I think it was 4.97. We took a measurement of that, you can see. And the other thing I did on this board here was grab the AC, bring it in, condition it through a voltage divider consisting of 2 resistors and a small, I think it's a 10 microfarad capacitor, just to smoothen the ramp a little bit, as this switching regulator seems to introduce a little bit of chop in it. The capacitor is smoothing that out, and then feed that into this Schmidt trigger here, 7414, and I just used a couple gates in that. And then on the unused gates on the other side, I pretty much just tied them to ground so they're not ringing. Open gates are bad. So out of this 7414, the final gate then gets fed into the board. A nice square wave at 50 or 60 hertz depending on where you're plugged in. And then from there, as we talked, our frequency divider here to divide it down the 50 or 60 hertz down to 1 pulse per second to start the counting chain to make the clock operate. And that's pretty much all the modifications on this Numitron tube clock here. There is a circuit here, schematic. And the modifications, I'll provide this along with the clock. I just covered up the original power supply drawing with my own hand-sketched high-end pencil drawing there and a little component layout board drawing to aid in future service of this clock. So that's it in a nutshell. I just wanted to go over it real quick, and when it gets to its destination, I hope you're watching. I hope you enjoy this clock. You know who you are. I thank you for everything, Peter. Okay, setting and operating of these discrete logic clocks, a little different. So we're going to power it up together and look to see how this thing behaves. It's an odd thing, but this is how these are. Okay, so look at seconds up to 77, 78, 79. Looks like a 4 missing a segment, but it's not. It's just all the counters are out of whack. So what you have to do to get these things to behave is just cycle the fast set for a period of time. Let's do that together, and you can see how this operates. Watch the hours, seconds, minutes, and all that. So it's going to count up 5, 6, 7, 8, 10, 11, 12, and rolled over to 1. That's good. So it's not abnormal to see the hours start counting 20, 30, sometimes 40 before all of a sudden it hits a point and the logic tells this section to, okay, go back to normal and start counting as a 1 to 12 counter. Final check before we connect power wires to the logic board. And we have our clock signal, 60 hertz. modification. It's going to work. And we're running just under 700 milliamps out of the wool transformer to the input of the jack on the back of the clock. Thanks for watching.